All right, good morning, everybody. What we're going to take a look at today is some more related rates problems. Hopefully you had a chance to go in and watch the video that I posted for Wednesday over related rates. I didn't want to just leave that topic with a video for you to watch, so we're actually going to do some more related rates problems today. It's one of the more important applications of derivatives in this course, so I wanted to make sure that I gave it plenty of time. I want to remind you of kind of the schedule leading up to the exam. So last night I posted the exam review. So if you go to the exam 2 assignment page, you'll see the review there along with the practice exam and practice exam answer key. There's a list of topics, a list of derivatives that you should know, and things like that. In thinking about the exam that's coming up, the main thing is being able to calculate derivatives. 20 to 30 points of the exam is nothing but calculating derivatives. So you have to be able to do that. You know, product rule, quotient rule, chain rule, all of that is on this exam. In addition, there's going to be a couple of word problems on this exam. You've got related rates that we've talked about. We just got finished with the latest skill quiz talking about particle motion, population growth, exponential growth. So there's going to be a good chunk of word problems on the exam as well. But take a look at that exam review, and if you have questions over the next couple of days, feel free to shoot me an email and we can chat about it. Monday in class, we'll cover the last topic that we need for this unit, which is the topic of differentials. It will be on the exam. It's not on the skills quiz. So the skills quiz that you have due for Monday is 2 related rates problems. It shouldn't take you very long to work through those, but go ahead and check that out. There are 2 related rates problems for you to do. Also, the homework, which is due Monday night, is not particularly long. There are only a couple of questions on that homework set. They deal with related rates and differentials. So make sure that you are on top of your schedule for this next week, as we do have the exam coming up on Wednesday. Do y'all have any quick questions for me before we get started? All right, well, if there's no questions, I want to start with a reminder, I guess, if you've already seen the video. And the reminder is what a related rates problem looks like in terms of the 5 steps that are involved. And as we go through the problems today, I'm going to continue to use the same 5 steps that you would have seen in the video on Wednesday. What I will do today that's a little bit different than obviously what I did in the lecture video for Wednesday is I will pause after we've drawn a picture together of the situation, which is step 1. And then in learning catalytics, I want you all to tell me what is the given rate and what is the wanted rate. I've found over the years that students that can do step 1 and step 2 correctly, draw a picture and tell me what rate is given and what rate is wanted. I've found that students that do those 2 steps correctly usually do the entire problem correctly. So if there's going to be an issue, it is typically with step 1 or step 2, just not being able to visualize it and or not being able to determine what rates are important. So a related rates problem has 5 steps. You're going to draw a diagram and label the quantities that don't change and the quantities that do change. And it's the quantities that do change that we're going to relate to one another. So, you know, if you have one side of a figure that is static, its value doesn't change, but you've got the other 2 sides of the figure which do change over time, the rates at which those 2 sides change is probably what we're going to be relating in the problem, hence the name related rates. Number 2, what you should do is tell me the rate that you're looking for, that's the rate that you want, and the rate that you're given. So on step 2, we're going to find the rate that we want and the rate that we're given. We're going to write those down using the notation that we've used to label the figure. Step 3, we're going to find an equation that relates the 2 variables for our rates. I'll talk about that as we go through the problem. Step 3 is where the math really starts here. Step 4, we're going to implicitly differentiate. So implicit differentiation skills are going to be at a premium here. You're going to have to be able to do that to do these problems correctly. And then 5, we're gonna solve for whatever the wanted rate is, and then analyze that answer in context. All right, let's take a look at an example. I have 4 examples planned for you this morning, and they are all different examples from the example types that we worked in the video on Wednesday. All right, so the first problem here, the sun is rising at a rate of 0.25 degrees per minute, and it appears to be climbing into the sky perpendicular to the horizon. How fast is the shadow of a 200-meter building shrinking at the moment when the shadow is 500 meters long? All right, let's draw the picture together, and then I'll give you a chance to tell me what the rates are that you want and the rate that you're given. All right, so first off, the problem says that we have a sun rising up into the sky that's casting a shadow on a 200-meter building. So if I was kind of drawing a picture for this, I'd go ahead and put in the building. So we've got this building here. We know, draw this out far enough. We know that there is a sun behind it. So the sun's over here. And the sun is rising perpendicular to the horizon, so we know that this is a right angle. And this is your building. You're told that the building is 200 meters tall. That is a static length. So if you're looking at the length of this triangle right here, this side always stays 200. But you can see that as the sun rises higher, right? So you might have a situation where the sun is really high up in here, right? The shadow length is going to decrease. So this side over here is the length of the shadow. And it's going to change as a function of time. And so I'm going to call this side x of t because it's on the horizontal axis. So x of t is going to be the length of that shadow as a function of time. So over time, what we observe is, so over time, x of t will shrink, which means that we expect dx dt, the rate of change of that length, to be negative. That's going to be a decreasing function. The length of the shadow is going to decrease. Okay, so let me take out the red here. We don't need that. This is the picture we're looking at. And the other part of this puzzle is it says the sun is rising at a rate of 0.25 degrees per minute. So that is the angle of elevation here. So that is the angle of elevation is rising. I'll call this d theta. I'll call this theta of t. So theta of t is the angle in degrees at time t. And it's rising at a rate of, let's see here, 0.25 degrees per minute. If you're looking at other parts of this problem, we're not told anything about this distance. So right now, I'll just kind of say, does this distance matter? And if it does, I'll call it L of t for the length of that distance. Maybe it matters, maybe it doesn't. I'll go ahead and label it. So those are all of the important parts of this problem. So what I want you to do now, so this would be considered step 1. You've drawn a diagram, you've kind of labeled the different parts. What I want you to do now is tell me, for this problem, which of the following correctly gives the rate wanted and the rate given. So theta of t is the angle of elevation, x of t is the length of the shadow. All right, yeah, about 20 seconds. All right, everybody that's logged in has answered. And the results, 2/3 of you are saying, well, 83%, excuse me, 83% of you are saying that the answer is A, which is correct. The angle of elevation is rising, hence positive rate, rising at a rate of 0.25 degrees per minute. And what we want to find is the length of the shadow, right? The length of the shadow, which is dx dt. We want to find its rate of change when the shadow is 500 meters long. So that's when x is the length of the shadow, when x is 500. A lot of students will always think about evaluating the derivative at a time value. And so the most common incorrect answer is typically B, because they're evaluating at a time value, or it's C, because they misinterpret the sign of the given rate. They misinterpret whether the given rate is positive or negative. Remember, positive derivative means the function is increasing over time. Negative derivative means it's decreasing over time. So if you go back to the picture, you can clearly see that the rate that you want is you want to find dx dt when the length of the shadow is 500, and the rate that you're given is d theta dt, which is that angle. As the sun rises, that angle gets bigger, therefore it's growing. So it's growing positive rate at a rate of 0.25 degrees per minute. So that's step 1 and 2 on every one of these problems. Draw a picture, list the rate that you want and the rate that's given. All right, so the rest of the problem is the math required to take you from the variable theta to the variable x and then solve when x is 500. So we want to use these two rates that are related by the problem to determine the wanted rate. So step 3 is to write an equation that relates the two variables. The variables here are theta and x. And if you look at our picture, what mathematical equation relates the angle theta to the length x using information that we have?
Tangent.
Tangent. Remember, tangent of an angle is opposite over adjacent, and we know both the opposite side and we want to solve for the adjacent side. So here the tangent of theta is equal to 200 divided by x. Now remember, just because I don't write theta and x as functions of t, they are functions of time here. So I'm simply hiding the function dependency, which means that if I take a derivative with respect to time of both sides, which is step 4, then I have to implicitly differentiate both variables. So anytime I take the derivative of one of these variables, I have to multiply by the derivative of that variable with respect to time. So the derivative of tangent is secant squared, but that contains theta, so I have to multiply by the derivative of theta with respect to time. The derivative of 200 over x, so I'm thinking of 200 over x as being 200x to the negative 1, and I'm using power rule. The derivative of that would be negative 200 x to the negative 2, which is negative 200 over x squared. But because it contained the variable x, which is a function of time, I have to multiply by dx dt. So we have implicitly taken the derivative in step 4. Finally, step 5 is I want to solve for the wanted rate. I want to find dx dt. Well, here's dx dt. I want to solve for this quantity. So doing a little bit of the arithmetic here, we would say that secant squared theta d theta dt equals negative 200 over x squared dx dt. And there's a couple of different ways I can go about this. I think my preference is to substitute in numbers and then do the algebra, or then do the arithmetic. So the first number that I have to substitute in, so I'm doing this, so solve for dx dt when x is 500. That's the rate that we want to find. So if x is 500, I can make this minus 200 over 500 squared. And on the left-hand side, d theta dt is the other rate that I was given in the problem. So d theta dt is a constant 0.25 degrees per minute. So I can substitute in 0.25 for that rate. And then I've got secant squared of theta, and I need to substitute something in for theta. Well, I'm looking at my picture, which is this triangle. Precisely when this side is 500 and this side is 200, I need to know what theta is at that point. So this is the picture we're looking at down here when we're solving for dx dt. I need to figure out what is my angle of elevation precisely at the moment where the length of the shadow is 500. So I'm going to go back to tangent for just a second. I've got tangent of theta is 2/5, 200 over 500. And I need to find the arc tangent, if you will. I need to find the arc tangent of this value. So theta is the arc tangent of 2/5. So this is just something that you would plug into Desmos. Let me do that real quick. All right. Oh, your professor messed up on something. I forgot an important point here. When you deal with angles, and I think I mentioned this in the video on Wednesday, when you deal with angles in this course and the derivatives, you need to always represent them in radians. So the unit of measure is always going to be radians. So if you have 0.25 degrees per minute, that's the same thing as 0.25 degrees per minute times 2 pi over 360 radians in degrees. This is the conversion factor for those two. So you're going to convert it to radians per minute. 0.25 times 2 pi over 360 will turn out to be 1/720th. This is radians per minute. The reason that's important is if you look down here where I plugged in 0.25, I shouldn't have done that. I should have had 1/720th as the value plugged in for the rate. Rates in calculus must be in terms of radians because that's how the derivative of an angle is defined in calculus. It's defined in terms of the radian measure of the angle, not in terms of the degree measure of the angle. So I mentioned that in the video on Wednesday, but I just forgot to do that here. So make sure that you jot that down in your notes, that this angle must be in terms of radians per minute or radians per second, whatever the time is. The time doesn't matter, but the angle measure should be in terms of radians. Sorry, the pi didn't go anywhere. It should still be there. Pi 7/20ths. All right, so now I need to figure out what theta is. I typed in arctangent of 2/5 and got 0.3805. And the reason why I need this measure to be in terms of radians is because when you plug this into your calculator, this number is going to be in terms of radians. So that's what clued me into the fact that I had messed up, is because you can't, technically I could do the problem with degrees, but then I'd have to convert this answer to degrees as well. Okay. So just make sure that you're either doing the problem entirely in terms of degrees or you're doing it entirely in terms of radians. And so what I generally advise students to do is always convert angles to radians. And then that way later on, when you're doing tangent, arctangent, secant, whatever sort of calculations those are, your calculator is going to naturally give you the radian answer. So we've got theta is 0.3805.
Where's the radians function on the, I mean, how do you switch? Oh, right there. Okay.
I
So you
was
go,
just about to show you that. Yeah. So in Desmos, it defaults to radians. So if you click the little wrench icon, it defaults to radians. So this number is in terms of radians. But yeah, you could work the problem with degrees if you wanted to from the very beginning, but you would have to convert every trigonometric function from then on to degrees. So to me, that's a bigger hassle than just converting that original angle measure, which is in degrees, converting that one angle measure to radians, and then just doing the rest of them as you would. All right, so you've got 0.3805 radians. And we'll plug that value in there. Okay, so now I'm just going to calculate out the values and solve for dx dt. So dx dt is going to be...
I'm sorry to interrupt. Where did the pi go when you convert it to radians?
It should still be there. I originally had it out, but it should still be there. It's pi over 720.
Okay, thank you.
Yeah. So you've got secant squared of 0.3805 times pi over 720 divided by negative 200 over 500 squared. That should equal dx dt. And if you want the pi symbol in Desmos, the easiest way to get it is type lowercase p, lowercase I. So type out pi, and it'll automatically convert to pi. All right, so there's what my calculation looked like in Desmos. Secant squared 0.3805 times pi 7/20 divided by this value. That's negative 6.33, let's say. So negative 6.33. So this is negative 6.33. And let's interpret that answer. What is this? What are the units of this answer? What does it mean? Does it make sense? These are all questions that you should ask when working a related rates problem. What do y'all think?
It's decreasing at 6.33 meters. The shadow is as the sun is rising.
That's correct. And the length here was in terms of meters, I believe. Yes. So negative 6.33 meters per minute. The shadow is decreasing.
Well, we have to, I noticed you did a few of your conversions in some of the other YouTube videos. Besides converting to radians, is there any other, especially in this course, that we have to worry about? Like, do we have to convert from meters to centimeters, or pretty much will the problem at this level just be?
No, I'm not going to get too involved in units. That, to me, that's really more the purview of a physics or engineering course. They'll involve units a lot more than we do. So this is one of the few occasions where I'm going to be insistent upon you paying attention to the units. In differential equations, we'll do some converting of units, but this is the one that I wanted to point out to you. So I think it's best to do the angles in terms of radians. All right, let's look at another example, and I'll pick up the pace a little bit because I'd like to get a certain number of examples done with you today. So example 2. And I think you have a question similar to this on your skills quiz. It's slightly different from this one, but it is similar. We have a 50-foot ladder that's leaned up against a large building. The base of the ladder is resting on the floor, and there's a small oil puddle at the base of the ladder that causes it to kind of slide away from the building, at which point the ladder's height comes down and it slides further away. I want to find the rate at which the height of the ladder is changing if the base of the ladder is now 30 feet away from the wall. So let's draw our picture, and then I'll let you tell me what's the rate that we want and the rate that's given. So our picture for this problem is we've got some sort of building or wall, if you will. Okay. And we've got a ladder that's leaning up against it, and we know that the ladder is 50 feet long. I'll call this, once again, x of t is the length of the ladder, or length of, or distance from, excuse me, distance from the building. So distance from building to the base of the ladder. And then similarly, I've also got this distance here, which I'll call h of t, which is the height of the ladder in feet. Okay, the angle is not important for labeling here because I'm not given any information about the rate of change of this angle. Technically, I could find that, and that could be another form that this problem takes. So Zach, per your question, expected to know formulas like areas. Yes, if they're simple figures, like things like triangles, rectangles, squares, but if it's trapezoid or something that's more just not mainstream, then no, I'll give you those. Same thing for volume, surface area, stuff like that. I don't expect you to know anything that's not just really simplistic. Okay, so what I want to do here is, now that I have the picture drawn, the other thing I'll probably say here is I know that the base, this point right here, I know that it's sliding away at a rate of 3 feet per minute. So this is my picture. So I want you to go in and tell me which of these is the correct rate that's given and which of these is the rate that is wanted. All right, yeah, about 20 seconds. All right, all the answers are in. And we have pretty much the same agreement as before. 83% of you said D is correct. So on D, you're given is that dx dt is 3. That's the rate at which the base of the ladder is slipping away from the wall. And what you want to find is the height, right? You want to find the height of the ladder when that distance is 30 feet away. So the height of the ladder after the base ladder is 30 feet away from the wall. So our wanted or our given rate is dx dt equals 3. And the reason that this is a positive 3 is because the distance here for x in feet is growing, right? As this base of the ladder slips away from the wall, the distance from the base to the ladder increases over time. So it's an increasing function, which means it has an increasing rate, or it has a positive rate. So the wanted rate here is I want to find the height of the ladder, specifically when that distance is 30 feet. So I want to know what is the height of the ladder on the wall when this distance is 30 feet, which means that I'm looking at eventually this picture here. So eventually the picture is this distance is 30, this distance is h, and this distance, because it's the ladder, is always 50. So eventually this is the triangle that I'm looking at when I'm going to solve for the problem. All right, so step 3, find an equation that relates the two variables. The two variables here are x and h. So going back to our picture, how can we relate x, the length here, the base of the triangle, with the height of the triangle? What's a mathematical formula which will give me x and h in the same equation? This is a right triangle, and that's important.
Theorem.
Yeah, Pythagorean theorem, right? So if you have a right triangle, side squared plus side squared is the hypotenuse squared. So we know that on this triangle, x squared plus h squared, those are the sides of the triangle, is going to equal the hypotenuse, which is 50 squared. So this is Pythagorean theorem. All right, so step 4, differentiate both sides implicitly. On the left-hand side, the derivative of x squared is 2x, but I've got to multiply by dx dt because x is a function of t. Then I have to do the same thing for h, so you get 2h, but since h is a function of t, I have to multiply by its derivative as well. On the right-hand side, the derivative of 50 squared. 50 squared is a constant. The derivative of a constant is 0. So now we get down to step 5. To finish out the problem, I'm wanting to find dh dt when x is 30. So I'm going to have to know, well, x is clearly going to be 30. I know the rate dx dt is 3. I don't know h. That's the one I'm going to have to find here in just a second. And I want to solve for dh dt. So let's go ahead and figure out what h is. And this is why I drew this triangle here, because at the moment we're trying to solve when x is 30, this is what the ladder looks like relative to the building. So I want to figure out what h is at that moment in time. There are many different ways to go about doing this. I will mention to you this is a right triangle. And so you have what are called Pythagorean triples. Do y'all remember what a Pythagorean triple is?
Yes, sir.
So this is actually a Pythagorean triple here, because if you have a right triangle, one of the ratios that's common is what they call a 3, 4, 5 triangle, meaning the sides are in a ratio of 3 to 4 to 5. So if you know you've got 3 and 5, you know this one has to be 4. In this case, 40. So I can pull from this that h is 40. If I didn't know that and I wanted to find h, then I could simply do 30 squared plus h squared equals 50 squared and solve for h. Are you talking about the 3 right here, O'Brien?
Yes, sir.
Yeah. We multiply by the 3 because dx dt is that rate is 3. So I'm replacing dx dt with 3 down here when I go to solve for dh dt.
I got you. Yes, sir.
Now h at this point, we just found that h is 40. So h is 40, plug that in. You got 60 times 3 is 180 plus 80 dh dt. And so dh dt is negative 180 divided by 80, which I get that to be negative 2.25 feet per minute. Okay, let's think about our answer. Does our answer make sense? Should the height be decreasing here?
I mean, the ladder's going down the wall.
Yeah. Yeah, since the ladder's going down the wall, the height, the distance h, this distance here should be closing down, right? As this base slides away, the top of the ladder comes down, so the height should be decreasing. And that seems like a reasonable rate, given that the ladder, the base is sliding out at 3 feet per minute. That seems like a reasonable rate. Yes, you can leave it in fractions, right? If you wanted to tell me like negative 9/4, that's fine. All right. So let's make sure we get at least a third example in here. So I'm going to go on to example 3. All right, so suppose you drop a stone in a pond, and if you were to chunk the stone in the pond, what it would do is it would send out sort of circular ripples. If you take differential equations someday, I'll tell you what the equation is for those ripples. It's actually a cool problem. Whose radius increases at a constant rate of 4 feet per second. So the rate at which the ripples of water are going outward from the splash point is 4 feet per second. After 12 seconds, how rapidly is the area enclosed by the ripples increasing? So I'm assuming that the ripples are circular, which in reality they pretty much are, depending on the surface tension of the water. So what we want to do is draw a picture of this, kind of figure out what's going on here, and then come up with an answer. So in terms of what this would look like, you've got the point where the rock is thrown. And you've got some concentric circles. So let me draw in a couple of circles. So these are the ripples that are going outwards. The function here, which is growing in length. The function here, the length of this piece. I'll call R of t. So R of t is the radius of the ripple made circle at time t. And time is in seconds. And radius is in feet.
We can't see the diagram.
Oh, sorry. There you go. So the rock is thrown into the pond. You've got these concentric circle ripples that form from it. And the outermost ripple, right? This outermost ripple that's created has distance from where the rock is thrown. I'll call it the radius of the circular ripple here. The radius of that is r of t. So that radius is increasing over time. All right. There's really not much more to write here other than to kind of write in what the rate is telling you. And it's telling me that r of t increases at a rate of 4 feet per second. All right, so based on the information given, I want you to tell me the rate that you want and the rate that is given. And we'll let A of t, let me kind of highlight this in here. A of t is this area in here. So we'll let A of t be the area enclosed by the outermost ripple. So if A of t is our area, R of t is the radius, tell me what rate we want to find and what rate is given. All right, you got about 20 seconds. All right, this time we are 100%. So the correct radius, dr dt, is 4. The radius is increasing. And I want to find the rate of increase of the area after 12 seconds. So this is our first one where we've actually plugged in the time. Both the other 2 examples, we did not plug in time. All right, going back to the problem, we know the rate that's given is dr dt equal 4 feet per second. And dA dt, I want to find after 12 seconds. Okay, so I need to find an equation that relates the area of a circle to the radius of a circle. And so per Zach's question earlier, this is something I expect you to know if you're in this course. The area of a circle is pi r squared. So step 3 was pretty easy here. What's different is A and R are both functions of time. So A is a function of time and the radius R is a function of time. So 4, if I want to implicitly take the derivative of both sides, the derivative of A is dA dt, and the derivative of pi r squared would be, well, it would be 2 pi r, that's power rule, but times the derivative of r with respect to t. So I've taken my derivatives. And step 5 is I want to solve for dA dt precisely when the time is 12. So dA dt would equal 2 pi. I need to figure out what my radius is at 12. And then dr dt, the rate, is given to us in the problem is 4. So if I want to know what the radius is at 12, what's a way that I have of doing that?
You can figure out what the radius is at time 1 and then multiply it by the time that you want to find. So it'll be 4 times 12.
Okay. So said another way, I like the way you said that. Said another way, our function r of t, we know r of t is increasing at a rate of 4 feet. The radius is increasing at a rate of 4 feet per second. So r of t is 4 times t, right? So 4 feet per second, right? So the function for the radius here is 4t. It's increasing at a rate of 4 feet per second. If I take the derivative of 4t, I get 4, which is our rate. So basically, I'm just saying that the function for the radius is 4t because the rate is 4. It's a constant rate of 4. So I know that r at 12 will be, just like CJ said, 4 times 12 or 48. Let's see, feet. So if I plug that in for 48, I get, let's see, 8, 320, 384. So 384 pi, and I'll just leave it like that, 384 pi feet. What are the units here for area divided by time?
Feet per second.
Yeah, feet squared per second.
I got a question, sir.
Yes.
Let's say they didn't give you the time or the radius at time 1. Let's say they gave you the radius at time 2. Let's say they gave you 8. How would you write that r of t function?
Well, the r of t function is based on the given rate in the problem. You're told that the rate at which the radius is increasing is 4 feet per second. And, that means you go 4 feet in 1 second, you go 8 feet in 2 seconds, you go 12 feet in 3 seconds, right? Does that make sense?
Yeah. Would you, so if, let's say they gave you the 8 feet per second every 2 seconds, would you just write r of t and then just kind of go 8 feet divided by 2,
Yeah.
something like that?
Yeah, exactly. So r of t would be 8 feet every 2 seconds.
Okay, there it is.
Covered in t seconds, right? So you can see that that's still 4t for the function there.
Okay.
Yeah. All right. So that's all we have time for today because we just hit 8:50. So we got in 3 examples. That's not bad. I think I got in 4 or 5 examples with you in the video on Wednesday. So all totaled, you've got about 8. And I tried not to do exactly any of the examples that are in the textbook. So you also have all the examples from the textbook as well as I think there's 2 videos that I have also. So this is the kind of topic that if you commit yourself to doing all the problems in the same order, just like I did, step 1, 2, 3, 4, 5, you do a lot of examples, look at a lot, then you'll be prepared for anything I throw at you on the exam. I'm not going to try to make it any more difficult than the questions that are on the skills quiz. So if you found that the skills quiz is something that you're able to do, then you should be able to do this on the exam as well. All right, y'all have a great weekend. If you have any questions about the exam, skills quiz, or anything like that, let me know. See you back in class on Monday.
Have a good weekend, sir.
You too.